In this video, we'll cover the problem min stack. Here, we want to build a stack class that has our typical methods, push, pop, top, which is equivalent to peek, and one special method called getMin, which allows us to get the minimum element of the stack. We want every function to work in O of 1 time. These typically work in O of 1 time on a stack, so we're not too worried about those. The key is, how do we actually track mins? Well, let's look at an example. Interesting. Okay. So here they're pushing -2 and then 0 and then -3. So at this time, the min should be -2. At this time, the min should be 0. Sorry, it should be -2 still. And at this time, the min should be -3. But it looks like after that, we get min, which should be -3. Then we pop, so we remove the -3. And then we get min here, so that time should be -2, which is what it is. And this 0 here just comes from the top after we pop. Okay, so typically the way we might do this is we might have sort of a min variable where we'd store, like the min, I don't know, literally just the min. And then we just kind of, whenever we push, we say, hey, am I smaller than the min? The key is that, so imagine we did that. You know what, let's actually draw out this example so that we can model things here. Okay, so we'd have -2, 0, -3. So first, let's actually go through this and track what the min would be. So initially, min is like, let's say null, or we can say infinity. Then we add -2, and it's like, okay, the min is -2. We add 0, the min is still -2. We add -3, and the min is now -3. So if someone asked us, hey, what's the min right now? We could just easily return it. But what if we were to pop this -3? Well, now we don't know what the old min was. We'd have to recompute it. We'd have to iterate over all these elements and find the new min, which is not acceptable because that's going to be O of n time complexity, where n is the number of elements in our stack. What we need to do is we need to store the history and say, okay, yes, -3 was the min right here, but we still want to know what the mins were beforehand. And so what we can do is we can actually use another stack to store mins. So let me show you what this looks like. So we'll have a min stack here, and then our real stack here. So initially we add -2, so then we say, all right, this is a new min. We add it to our stack, or our min stack. Then we add 0. Well, that's not smaller than -2, so -2 is still the min. Then we add -3, and -3 is a new min, so we add it here. So if someone asks us right now, what is the min? Well, we just grab this top element from the min stack. If somebody popped -3, what we can do is say, oh, look, we also have a -3 here. Let's pop that. And now if someone asks us for the minimum value, we can just look at the top of our min stack again. So this works and allows us to do everything in O of 1 time. And we're kind of storing the history of all of the mins in our min stack so that whenever we pop elements, we know our old mins. The last thing I want to mention is what happens when we have multiple of an element. So for example, say someone had -3 again. You may think we don't need to add this here. However, we actually do. Because imagine that we did not add it, so we just had this kind of scenario. Then somebody pops the -3. Well, we're going to look here and think, oh, we should pop this -3. So we're going to get this output, which is not correct, because -3 should be the min, not -2. So we need to account for the fact that we have multiple versions of this element. So if we're pushing something that is equal to the top of the min, we still need to push it. Okay, that is all in terms of conceptually understanding what we're going to do, so we can go ahead and code it out. I'm going to clear all of this and write this with class notation because that's what we would do in a real interview. Oh, okay, it deleted everything. So we need a push, which takes in, I forgot what they called it, but I'll just call it element. Pop. Maybe I'll call it new element to be a little more precise. We have pop, we have top, we have get min. Okay, so what we're going to do here is we're going to have two stacks. We're going to have a stack, we're going to have a min stack, and in JavaScript we can just use an array for a stack. Also, one thing we're going to be doing is getting the last element in our stacks, equivalent to peeking. I'm going to write a function to do this, just so that we don't have to do it too often. Or we don't have to keep rewriting the code. So we'll get the last index, which is going to be array dot length minus 1, and then we're going to return array at the last index. Note that I'm writing this outside the class because this is a generic function that can be reused. Okay. Now, let's see. Are there any easy methods we can do? Well, getting the top of the stack is pretty easy. We're just going to return a get last element of our stack. And that runs an O one time. To get the min, we do the same thing, but we want to use the min stack. So we'll say get last element of this dot min stack. Okay. Now we want to handle our cases here. So let's see, how are we going to push? Well, first of all, we know we're going to push to our stack always. Dot push the new element. The question is, when do we want to push to our new stack? Well, we want to push, remember, if the new element is smaller than our current min, or it is equal to the current min. And the current min we get by just doing this dot get min. So we can say if new element is less than or equal to this dot get min, then we should be pushing to the min stack. Like so, dot push new element. I'm actually going to put this in curly braces because this is going to get a bit large. There's one other thing we're missing here, which is that sometimes min stack will have a length of 0, and we should just always push this because it's our new min. So we'll say if min stack dot length is 0, or the new element is less than or equal to our current min, then we push. This is also good because if we tried to call get min when the stack length is 0, that would cause problems. Maybe just to be more explicit, we can explicitly handle this. So we can say if the size is 0, we'll throw an error, say cannot get min, stack is empty. And we should do something similar when we're doing our top right here. So we'll say cannot get top, stack is empty. This should be this dot min stack. Okay, so that should be our pushing logic. So we always push to our normal stack, and we're going to push to the min stack if we have a new min, meaning either we don't have any mins or the current number is smaller than or equal to the min. Okay, now to pop, let's see. We are definitely going to pop from our real stack, so this.stack.pop. One thing that's a little weird is they don't want the pop to be returning anything. That's what this void means here. Normally pop returns the element that you pop, but I guess here we don't have to. But we also need to make sure that we pop from our min stack when we should. And we should pop from the min stack if we are popping the value that is currently the min. So what we can do is check the last element of the stack and the last element of the min stack. So we can say if this dot top is equal to this dot get min, then we want to pop from the min stack, because this means that the element at the top of our stack is also our current minimum. So we need to say, hey, this is not a valid minimum anymore because it's not in the stack. So we pop right here. Okay. So this looks like it should make sense. The one other thing I would do is I would add a check that's like, if the stack has no elements, then we should be throwing an error as well, and we'll say cannot pop, stack is empty. Okay, I believe this should be all the logic, so let's go ahead and see if this works. Okay, it works here, and if we submit, great, it works there as well. All right, well, that's all for this video, and thank you for watching.